Okay, so hello and welcome to our first virtual lecture from the Institute of Physics West Midlands Branch. We are about to start and I'm absolutely thrilled to welcome Dr. Aaron Jones and Dr. Sam Cooper. Please you just note that your webcam and microphone are disabled at the moment. When we move on to the next page, we will just have some instructions on how you can ask questions. Wonderful, thank you. So if you want to ask any questions, there is a chat box and a question box. And if you look here, you can see the controls for the microphone and the webcam, which are actually just for the for us. You have got those disabled, but there should be a chat image for you where you can add, and also a question which you can look at. And I will just see if I can see this on here. Certainly can see. So where you have questions, you have got underneath the bit which you've got quite a big section which says type your question here. We will monitor those questions as we're going through and either put them to Sam and Aaron or else we will have a question and answer section at the end. We will try and have closed captions available during this broadcast, but if that doesn't work, we will be making a recording of this webinar. And there will be captions on the recording. So if for any reason you would like to have a copy of the captions, the recording with the captions, then please do let us know and we will be able to organise that quite straightforwardly. Thank you. Okay, perhaps the next slide, please. So what we're going to hope is everybody who is on our mailing list has already had a copy of our programme. If not, then we will have the information on www.iop.org, Physics Community, IOP membership where you are, West Midlands. I will actually be dropping the links in the chat as well. I'm not absolutely sure if you can save the chat. Sometimes you can, sometimes not. Otherwise, maybe just copy and paste the chat. I will also be dropping information about individual lectures as they come up, our next events, in the chat as well. I'll also give you some information about the Gravitational Alerts app, which Sam and Aaron developed, called Chirp, and they'll be talking about that as part of this session. I think that's probably everything, but please do use the chat and the questions to add any information that you want us to look at. I'm actually, the reason I'm looking across, by the way, is just because I'm checking my screen where I'm also on as a participant as well as an organizer. So perhaps, Sam, if you could do the next slide and I will introduce you both.
That was the wrong button.
Okay, so
I think that's one.
This is coming through. It's coming through slowly.
Okay.
Wonderful. So we're welcoming Dr. Sam Cooper and Dr. Aaron Jones, who are going to give our talk this evening. And the IOP West Midlands branch first came across Sam and Aaron when they were researchers at the Institute for Gravitational Wave Astronomy at the University of Birmingham, showcasing their mobile app Chirp, that allows members of the public to stay up to date with the new gravitational wave events detected by LIGO in the USA and by Virgo in Italy. I believe Sam was inspired to develop the app to showcase his work to his young cousins, who actually would rather he did not work and he came and played Mario Kart with them. Sam's doctorate is in sensor development and controls for future gravitational wave detectors from the University of Birmingham. He's currently working at the University of Birmingham as a postdoctoral researcher on compact displacement. He's a member of the LIGO collaboration and author on over 80 publications, including full collaboration papers. So thank you, Sam. Aaron's doctorate is in laser technology for precision devices, also from the University of Birmingham. He's an experimental laser physicist and computational modeler, and he recently took up a post as research associate at the University of Western Australia, working on prototype technology for the third generation gravitational wave observatories. However, he is actually still sitting in the UK due to problems with a visa. He's a member of the LIGO collaboration developing next generation technology and is the author of 40 publications as well. So welcome to you, Aaron, as well. And we shall look forward to hearing your talk. Thank you.
Thank you. So gravitational waves are a really exciting new way of observing the universe. So the first gravitational wave detection was only in 2015, and we're really excited to be with you today and talk about some of these exciting results and also some of the technology, which is what Sam and I work on, which we use to detect it. So Sam is going to talk to you about in a second how this work is not just our work, but the work of everyone in the collaboration.
Thanks, Aaron. So thank you for the warm welcome, Nikki. I'm really glad to be able to give this talk. It's kind of a childhood dream that I'm a scientist for when I first looked through a telescope when I was 6. But now onto gravitational waves. This work isn't just the work of myself and Aaron. It's not even just the work of our respective institutions, being Birmingham and Western Australia. It's a result of work from thousands and thousands of people, scientists, technicians, engineers who work tirelessly to try and make these gravitational wave detectors work and to understand the data that comes out of them. So these are just some of the people that are in the people and the collaborations which are in the LIGO scientific collaboration. And I should mention as well, there's also Virgo and Cagra collaborations as well. To give you an idea of the scale, there's about 1,300 people, I think, at the moment on the LIGO Virgo Cagra author list, and this is really a global effort that's supported by multiple funding agencies. So to give you an idea of what we're going to talk about, first we'll introduce Einstein's universe, and then we'll go into what astronomy you can do with gravitational waves, how we then detect them, then what we've seen, and then we'll talk a little bit about our app Chirp. So gravitational waves are distortions in space and time, and they're emitted by any masses which accelerate. And it doesn't matter how massive the mass is. So by me moving my hands around each other like this, that is generating gravitational waves. If me and Aaron were on a stage together, I'd grab his arm and we'll dance around each other in a circle, and that would generate gravitational waves. But these are incredibly small, the waves that would be emitted, and we couldn't hope to detect them with a gravitational wave detector. So we need to look at more massive objects out in the universe. So this image is of the life and death cycles of stars. So you may think that stars like our own sun, which have masses of around 3 by 10 to the 30 kilograms, this is a 3 and 30 zeros after it, kilograms, I think that's enough zeros, that they'd be massive enough to detect gravitational waves. But with the current technology, they don't generate enough waves when they're orbiting each other in binaries, which we'll talk about later. So the whole left-hand side of this chart we'd have to discard. Which then brings us on to what we can detect, which is the remnants of massive stars. And by massive, I mean these stars have to have masses of around 8 or 10 times the mass of our own sun. And these evolve over billions of years and burn through different elements. And a star's lifetime, there's 2 main forces which determine how the star forms. There's the gravitational force, which tries to compress the star down and down into a single point. And then there's a radiation pressure force, which is a result of all the nuclear fusion that goes on, where hydrogen, helium, and heavier elements are burned. And as the star evolves, it will then grow in size as it burns through different elements. Though, it can only do this up to a certain point, which is when the star tries to burn things that are heavier than iron. Because at this point, the nuclear fusion reactions don't give off enough energy to sustain the reaction, so the reaction dies. And then with the radiation pressure force being smaller, gravity then takes over and compresses the star down. These stars can then undergo supernovas, where the outer layers of the star get ejected in a big flash of light, which we could detect on Earth. But then there's 3 things that can then happen. One is that they could form star-forming nebulas, and the entire process can start again. The other 2 that we're interested, though, are in neutron stars and black holes. And neutron stars are interesting because they're still made of regular matter. They're just comprised, we think, of neutrons. And there's a limit to how much and how many neutrons you can pack into a certain volume, which is caused by neutron degeneracy pressure. So gravity then fights against this. And if gravity can't win against this neutron degeneracy pressure, then the star turns into a neutron star, or the core of the star does. If gravity is stronger than than this degeneracy pressure, though, gravity keeps on crushing the star down into a tighter and tighter, more compact object, and it then forms a black hole. And now Aaron will tell you a bit about how Einstein thought about gravity.
Now we need to use Einstein's theory of gravity because in the earlier theories of gravity, they weren't sufficiently accurate to model gravitational waves. So Einstein describes gravity as being a stretch of something called space-time. And it's a little bit like the stiff sheet you can see on the screen. Very heavy objects make a really big dent in space-time, and lighter objects make less of a dent. And this means that and when you try and escape a gravitational pull, you're getting higher up on this space-time curve. So if you jump right now, you're adding energy to overcome the curvature of space-time. Now on the next slide, you'll see that the curvature of space-time changes for different kinds of stars. Now all of these objects weigh approximately the same mass. They're all of order the mass of our sun. So a sun-like star is the mass of our sun. But it only makes quite a small dent in space-time. And this is because the density of a sun-like star is about the same as the density of water. Now, whilst the sun is incredibly heavy, as Sam alluded to, it does make a dent which is measurable. And you can see this by looking for a change in the orbit of Mercury. But it's not a dent that's big enough for us to measure gravitational waves from. For something like a white dwarf, this is again about 80% of the mass of our sun, so similar kind of mass, but it's condensed into a ball that's the size of the Earth. So it's much, much more dense. But again, if there were two white dwarfs orbiting each other, we wouldn't be able to detect gravitational waves from them with our current technology. It takes something that's one of the densest objects in the universe, and these are neutron stars and black holes. Now, neutron stars might weigh a few times the mass of the sun, so they're a little bit heavier, but they're about the size of a city. And so on the image at the top of your screen, you can see the Chicago skyline. This is because the artist that drew this is from Chicago. And then you can see the curve, and this is to scale the size of a neutron star. So these are really heavy objects. They're heavier than the sun, and they're condensed into the size of a city. Black holes, a stellar mass black hole is even denser still, but roughly they're the same density. Now, when you get these really strong curvatures, you can get tears in space-time, and these are the sorts of things that are dense enough for us to measure gravitational waves from. And on the next slide, there's a representation of what this means. So in 1905, Albert Einstein came out with his very famous theory, the special theory of relativity. And if you've heard the expression E equals mc squared, this is actually where this theory is where that comes from. He stated that mass and energy are equivalent and are related by the number, the speed of light squared. He then advanced on this theory to bring gravity into it. And this is where gravitational waves are predicted, because he says that in very curved areas of space-time, where you've got a very heavy mass, time runs slower and lengths become contract. And when it loads, you'll be able to see this in the animation, because the clocks that are very near the heavy mass are going to be running slower than the clocks that are far away from it. And then you can imagine all of these, the distance between these clocks, they're all the same distance. But when you go very close to the mass, that distance shrinks down. I don't think we'll wait for this video to load. On the next slide, Sam's going to tell you about some astronomy that we can do with gravitational waves.
So just like we can see different things about our own sun and stars and planets by looking at them in different lights, we also want to try and look at things in gravitational waves. So if we take optical light for a quick example, we can see in ultraviolet light, you can see these coronal mass ejections where plasma is being flung off from our own sun. But then if we look at things, if we look at the star in the visible light and in the infrared, we can see these sunspots. And these are areas of where the sun is a lot, where the surface of the sun at that point is a lot cooler. And when we try and look at things like neutron stars and gravitational waves, with a neutron star, we have to know where it is to be able to observe it. But then we can still observe it because we can see light from it, as we'll see later in the talk. But for black holes, this is a lot more complicated because they're so massive that light can't escape from the surface, from the event horizon. So this is a photo of a black hole. Hopefully people will have at least seen this before. But for those that haven't, this is an image taken by the Event Horizon Telescope collaboration of M87. This is a super massive black hole, which has a mass of about 6.5 billion times the mass of our own sun, which is absolutely fantastic. I can't explain how excited I was when I first saw this image and when they released it. But if we want to see other sizes of black holes, if we want to see stellar mass black holes, i.e. black holes with a mass of around that of our own sun, we'll need to look at other things. And you can only really see these black holes when they're either accreting matter, i.e. they're eating stars and gas and planets or whatever's out there in space, because it causes the matter to become superheated and to glow. You can look at them if you want to look at a black hole. You can also look at the effects around the black hole, a gravitational lensing. But if you're wanting to look at multiple black holes that are orbiting each other and the effects of them, and to test general relativity and a bunch of other really interesting science, gravitational waves are a great way to do that. So if you remember the view of space-time, which is that space around a massive object the space around a massive object is curved. But with gravitational waves, when a black hole moves, the movement of the black holes around each other emits gravitational waves. And we usually talk about this in a sense that they're like ripples on the surface of a pond. But like all analogies, it doesn't quite fit the bill. But it's a nice way of visualizing what's going on when these black holes are orbiting each other. So on this next slide, you can see what a gravitational wave actually does. So hopefully if this video loads, you should be able to see this. The video in the bottom right-hand corner of the screen is just of a ring of particles as a gravitational wave passes through. And what the wave does is it causes the space between objects to stretch and to squash. And I think if the video in the top left loads, this will show you how a gravitational wave propagates in 3 dimensions. But the main idea is that gravitational waves will cause the distance between objects to stretch and squash. And then using this, we can then hopefully detect them because there's something unique to gravitational waves that we can try and isolate, and then we can try and design something that we can measure. And Aaron will now talk you through a simulation of what this will look like.
Yeah, so as Sam said, if you've got one black hole, you wouldn't be able to measure that change in space-time. But if you've got 2, then the black holes are continuously fighting with space-time to warp it as they move around each other. And that's exactly what you've got in this video. The 2 black holes are orbiting around each other. And as they orbit, they cause this dint in space-time which ripples away. Now that carries away energy from the system, which means these black holes falling closer and closer towards each other, and they speed up as they do so. That means they go around each other faster and faster, so they emit more gravitational waves, which mean they fall in closer towards each other, and so the gravitational wave amplitude increases, and so on and so forth, until they're traveling very close to the speed of light. And remember, these could weigh up to sort of a few times the mass of our sun. They could be as heavy as 30 times the mass of our sun, traveling at half the speed of light. And when they eventually collide, they cause a tremendous tear in space-time, and then eventually it'll settle down to a steady black hole again. And when the video zooms out in a second, you'll be able to see the gravitational waves rippling away. And that's illustrative. The color here tells you how big the stretch and squash was. On the next slide, we'll tell you some things we can learn from studying binary black hole mergers. Now, this isn't exhaustive. It isn't everything we hope to learn, but it gives you a brief idea. And so by counting the number of binary black holes that we observe, we can create models for our universe, and we can compare these to the models we have that tell us how many binary black holes we expect to see. You might say, why is this important? Well, this is important because by studying these, by formulating these models, we come up with ideas for how the early universe formed. And these models, they're based on our understanding of physics. And so by studying binary black holes, we can learn about the early universe, we can learn about how the first stars formed. We could also ask, how old are these binary black holes? Because if we observe black holes that have been orbiting around each other for since before the first stars were formed, then we know that these black holes weren't formed from stellar evolution in the way Sam described on the first slide. And that would be really interesting if we observed that. We haven't observed it yet. We don't know if we will. And if we don't observe it, again, that's really interesting. That tells us that all black holes are probably formed in this way. We can also look for unexpected things. So we know that the standard model of particle physics doesn't exactly match general relativity. And so we can then inspect general relativity in this really strong regime and look for anything new. And to give an example, the last time there was a real significant change in physics was probably the development of general relativity and the development of quantum mechanics. And those two things have led to the information era, which we're now enjoying. So by studying binary black holes, maybe we'll get lucky. Maybe we will discover something new and society may move forwards again. So I'm now going to talk a little bit about how the instruments we use to detect these gravitational waves. And on the next slide, you'll see a character called Al-Haytham, if I'm pronouncing this correctly. Now, he was a genius and a polymath. He studied a range of subjects. But the reason I'm talking about him now is because he is, as far as I'm aware, the person who proposed that light was composed of waves. This really bucked the trend because prior to him, the Greek philosophy was that vision was created by particles which beamed out of our eyes. And his theories, which were based on mathematics and rigorous experiments, showed that actually light is probably composed of waves and it enters our eyes instead of being beamed out from them. So this is really interesting because this means that light would undergo interference, which is described on the next slide. If you have two waves, they can either add up such that the peak of the wave arrives at the same time, or they could arrive, the peak could arrive exactly with the trough of the other wave. And you can imagine this like water waves. Either if they arrive at the same time, you get a bigger wave. And if they arrive at different times, you get a smaller wave or no wave at all. And it's the same with light. When you get constructive interference, they arrive at the same time, you get a bright spot. And if they arrive at different times, you get no spot at all. And this is one of the principles technologies in the Michelson interferometer. Michelson and Morley, again, absolute fantastic scientists. They developed their namesake instrument to look for something called the ether. Now, the ether was some absolute reference frame, and scientists at the time thought that you could measure everything with respect to this ether, and they thought that light traveled in it. Now, Michelson and Morley, they set out looking for the ether. They didn't find it, but then they went one step further and conclusively disproved it. And the absence of the ether led to the widespread acceptance of general relativity. So you can see how their instrument works on the next slide. Light travels out from an argand burner, and it hits this mirror in the middle, and the light is reflected in two directions. Now, if the light was traveling in an ether, then some of the light would have to go further than the other arm because it would have to travel through the ether. And this is the premise of their experiment. Now, they didn't find the ether. It did lead to the general theory of relativity. But what's really interesting is this is also the same technology that's used in gravitational wave detectors. So this is explained on the next slide, where there's a short video. Now, this video is using a laser instead of an argand burner. This is just because typically Michelson interferometers use a laser to suppress technical noises. As you can see, as the mirrors move, the light adds up towards the screen, either in phase or out of phase. So here we have a visualization of the light waves traveling out towards the mirrors. Then they get reflected back from the mirrors, and they meet at the beam splitter. And you can see them adding up out of phase. And when we move one of the mirrors, which you'll see in a second, the waves will start adding up in phase and we'll get light. And then we can just measure the amount of light here. And if you have some stretch and squash of a gravitational wave passing through, then it'll stretch and squash these arms and you'll be able to measure gravitational waves. If you had a Michelson interferometer traveling through an ether, then one arm, the light going in one direction would have to travel further than the other arm, and you'd be able to prove or disprove the ether. Now, Michelson and Morley did their initial experiment, and they didn't find the ether, but they knew that their experiment wasn't sensitive enough to conclusively disprove it, and so they improved the sensitivity. There were two issues that they tackled. The first one is seismic isolation. So you might think that the ground is very stationary. It certainly feels stationary to me. But actually, the motion of horses and carts and trains and waves hitting the shore is enough to cause small vibrations, which are typically about a micrometer in amplitude. And Sam will tell you more about that in a second. So what they did was they suspended their entire apparatus on a huge stone, which was 1.5 meters wide. And then they floated this stone into a pool of mercury to seismically isolate it and stop these mirrors wobbling about. But this still wasn't quite enough, and so they bounced the light backwards and forwards between pairs of mirrors to increase the path length. And the reason I talk about this is because these are exactly the same tricks we use in gravitational wave detectors today. They're more advanced, but it's the same basic idea. Now, on the next slide, Sam will tell you more about some of the length scales involved and how we need to improve gravitational wave detectors.
So now that we have a technology which we can use to try and detect these stretches and squashes in space-time, we need to make something that can actually, work and have multiple of these detectors which can work at the same time, crucially. So to give you an idea about length scales, we have people here, they're about a meter or two tall. I'm only going to use orders of magnitude, so I won't get too into detail on the exact numbers. You've then got things like the tip of a pencil, which may be a millimeter in size, which is 10 to the minus 3. Some people may even use these vernier calipers, which can measure down to about a micrometer, which is about how much the Earth typically moves. Due to waves hitting the shoreline. But to detect gravitational waves, we need to go smaller still. So then we get down to sort of nanometers, which is shown by the image in the bottom left-hand side of the screen. And this is it's around the limit of what people and what humans can manufacture things down to. So this is things like the transistors in CPUs and in mobile phones and those types of things. And we need to go even smaller than that. We need to go smaller than atoms, which are around, an atometer, which is 10 to the minus 10 meters, or a tenth of a nanometer, to a hundredth of a nanometer. That we need to go even smaller than this. We need to go even smaller still than a femtometer, which is around 10 to the minus 15 meters, or about a millionth of a billionth of a meter. And gravitational waves typically sit all the way down at the bottom of the screen at about 10 to the minus 18 meters, which is about 1,000th the size of a proton, the classical radius of a proton. So we need to make a detector which is this sensitive Now, Michelson and Morley's experiment, in their paper, they claimed that they could see a resolution of about a nanometer, which sounds kind of reasonable. We built some simple Michelsons in our lab to show to on outreach exhibitions and things, and a nanometer doesn't sound implausible. But we need to make this thing 1 billion times more sensitive to even hope to see a gravitational wave detector. So how do we do it? Well, these gravitational waves, they come to us in something called strain, and this is just a change in length per unit length. So the idea would be, if we can make this detector longer, so instead of Michelson's and Morley's detector being around 1 meter in scale, if we make this detector a lot bigger, then we should be more sensitive to this gravitational wave, because we need to make the mirrors move less in comparison to the length. So the two LIGO detectors, which are in Hanford, Washington, and Livingston, Louisiana, they're about 4 kilometers in length. So we should be 4,000 times more sensitive to gravitational waves just to start off with than if we just had a 1 meter Michelson, very simplistically. But as we saw from the last slide, this still isn't enough. We have to make the detector even more sensitive than that. And this is something that's still kind of mind-boggling to me. I should add as well that there's two other detectors called Virgo, which is based in Italy, and Kagro, which is built underground, that's built in Japan. Both of these detectors are 3 kilometers long. They're not as long as LIGO, but they're limited by local constraints, but they can still detect and should still be able to detect gravitational waves. So how do we make these detectors more sensitive? Well, just like Michelson and Morley went back to the lab and tried to make their experiment less sensitive to seismic motion, we need to think about any other different type of motion that could affect them. So this shows you a couple of images from what it's like on one of the detector sites. So the image on the left shows one of the test masses, one of the mirrors that you saw in the previous slides, which you bounce the light off and then hope to use to detect gravitational waves at the end of the detection path. Now these mirrors, they weigh about 40 kilos. I'm putting my hands up on the screen. They're about this kind of size. They're about 40 centimeters to half a meter across, roughly. Again, rough kind of scale. And each detector has 4 of these mirrors in its configuration, and they're suspended on 4 stages of isolation, on 4 stages of pendular suspension systems. And this tries to reduce the amount of seismic noise caused by the Earth hitting the shore and the Earth crashing into each other, which sends a pressure wave through the Earth's crust and shakes the ground at the detector. And remember, this is about 1,000 billion times bigger than the gravitational wave signal that we're trying to detect. There's also things like residual gas noise. So the air, you can fan yourself if you're getting a bit hot, and you can feel on your face the air hitting it. Gravitational wave detectors have the same problem, not because somebody's waving a bit of paper at the test masses, but because of just the random motion of the air particles which knock into the mirror and cause noise. So this 4 kilometer long vacuum tube that you see in the picture on the right is under vacuum. And this is about 1 billionth of atmospheric pressure to try and reduce this noise down. There's then other things like thermal noise, which is the random motion of the of particles in the mirror coating, and in the suspension, which you also have to try and reduce as much as possible. And another one is the radiation pressure, because as we take a laser beam and we shine it on a surface, this light has a momentum and it will impact a force onto the mirror and cause the mirror to vibrate. So we make these masses as heavy as we can do, and heavy as we can suspend, to try and mitigate this effect. So just like Michelson and Morley had to suspend their interferometer on a pool of mercury, we have to do the same, but we don't use a pool of mercury. Things get a bit more high tech. And this is one of the things that I work on, which is new sensors for these isolation tables. So there's a couple of scientists, one of the LIGO sites there for scale, and this detector, or this isolation bench is suspended on a set of steel blade springs, which passively isolate the table where all the suspensions are either hung from or stood on top of from motion on the ground. These have either one or two stages. They have a wide variety of displacement sensors, so things that just measure how far two objects are from each other, and seismometers that you'd use to detect earthquakes and things like this. And all of this is bundled together to try and isolate the gravitational wave detector from the ground. Another stage of this is the suspension systems, which I alluded to before. And there's 4 stages to these in the main test mass mirror arrangements. But the lower 2 stages are made of fused silica, and the suspension wires, the fused silica suspension wires, which hold the last stage of the suspension from the previous stage, are made again out of fused silica. And this is to try and reduce the thermal noise and the vibration of the atoms in the silica itself from interfering with the readout. These are developed by the University of Glasgow, who I'll thank for this image. And then on the left-hand side of the screen is something a bit more close to home, which is being developed in the West Midlands at the University of Birmingham, which is a shadow sensor, which is used to detect how much the suspension stages are moving. And I'll now pass it back on to Aaron to tell you about some of the other things that we have to do to try and make the detector sensitive enough to detect gravitational waves.
Yeah, so as Sam said, the signal is really, really weak. And so one of the things that we do is we make the laser power as high as possible. Now, you eventually reach a point when you can't increase the laser power anymore, because as Sam said, light has momentum, and this momentum hits the mirror. And there's some quantum mechanical uncertainty in when this light gets to the mirror. And this causes the mirror to just jiggle about an ever so tiny amount. But this actually is limiting the detector in its most sensitive region. And so we're in this region where you can't increase the laser power anymore. So you then need to turn to advanced techniques. And this means that every single photon counts. If you're losing photons from your measurement, so if you're losing any light from your measurement, this means that that light has caused noise in the detector, but it hasn't contributed to the signal. And so this is what I research, is sensing schemes to very carefully focus this light between each of the mirrors in the detector, and to make sure it's all connected together and it's all operating at the right point. And again, this research is close to home. A picture on the screen shows me during my PhD, and that's actually my lab, which was based in the West Midlands, again at the University of Birmingham. And here I'm doing an experiment where I'm looking, how can I read out this quantum state of the light? How can I find out exactly what the spatial state is, and then feed that back so that it's focused and so that there's no error and we're not losing any light in ways that we don't want to. And so on the next slide, you can see a picture of the detector, and there's a video in the top left. This shows this is going to be a video of LIGO Livingston and a gravitational wave passing through, and as you can see, it stretches and squashes. Just to remind you about the stretch and squash Sam talked about earlier. And then you've got this Michelson interferometer, the same device that Michelson and Morley used, only this time we've added some components to it. So on the next slide, there's some annotations, and you'll see that the state of the shape of the beam is cleaned before you go into the interferometer with this pair of 3 mirrors. This pair of 3 mirrors just makes sure that the spatial state and the longitudinal, these quantum states of the laser, are perfectly matched and ready for the interferometer. Then the light passes in through this beam splitter and travels in the 2 arms where it accrues this phase, which depends on the gravitational wave. Now, Michelson and Morley reflected the light between mirrors backwards and forth. We go one step further here, we reflect it between the same pair of mirrors, and so the light builds up in these arms, and we get several hundred kilowatts of light resonating in these arms. And then when the gravitational wave passes through, the light's reflected and passes towards this beam splitter. And then, yeah, there's this, as I've said a few times, we've got to really make sure that this quantum state is perfect. And that's why we change the vacuum state of the interferometer. We make sure there's no stray photons coming in backwards that could interrupt the measurement. And so we prevent these photons from coming in backwards by putting something here at the output of the interferometer. And this is really important because a gravitational wave, even though we have several hundred kilowatts of light in these arms, only produces about 200 photons for us to measure.
And it's worth remembering through all of this that all of this is under one vacuum system, and all of these different optics are grouped together onto isolation tables that I showed before, and each of those are independently isolated. And there's very, very fine tolerances of about somewhere between a picometer and a femtometer, that type of range, where the mirrors have to be held over for all the control signals to then keep the mirrors in check. So then they're able to, so the light's able to bounce between these mirrors so it can build up the gravitational wave signal. And this took, LIGO was built, I think, in the mid-1990s, and it took until 2015 for this detector, for the LIGO detectors to actually detect a gravitational wave. So there's an enormous amount of technology and engineering that's had to go in to make these detectors work, and still is required to keep these detectors work. So now I want to talk about some of the discoveries. And as a disclaimer, we won't talk about every discovery because there's frankly quite a few of them. But if you want to find out more about all the different detections that we've seen, there's a web link on the slides, ligo.org/detections, where you can find out more about this in more detail. So I want to start with observing 1-1, not just because it's the first one, but it's probably still my favorite gravitational wave detection. So on the 12th of September 2015, the two LIGO detectors in Hereford and Livingston were turned on in their advanced state. That's why you might see the detectors named Advanced LIGO and Advanced Virgo. And then 2 days later, on the 14th of September 2015, when I started my PhD, we detected gravitational waves. Well, I say we, but LIGO detected gravitational waves. And on a personal note, when I joined the group in Birmingham, it was around to the hour when the detection came through, and everything was started like a normal new job. You're meeting lots of people, you're learning lots of new things. And then over the next few days, I remember very clearly that people then started to have hushed conversations and started talking to each other and were very, very excited. And you could tell that something had happened, but I didn't know what at the time because I hadn't joined the collaboration. A few days later, I then learned that we'd actually detected two black holes, which were 29 and 36 times the mass of the sun, which spiraled around each other and collided. And to me, this was absolutely incredible that all of these things had lined up, and that I was able to be a part of that and to see all of the work and all of the cross-checking that went behind making this detection to really confirming this detection. And when these two black holes merged, they formed a 62 solar mass black hole. And this occurred around 1 billion light years away, so this is about 1 billion years ago that these black holes merged, and it took this long for the gravitational waves to reach us. These black holes collided at about 60% of the speed of light, and they emitted 3 solar masses worth of energy as gravitational waves, which is really quite incredible, I think. And I'll go into this more in a slide or two's time. So this animation on the left shows what this looks like. So you have two black holes which are orbiting around each other, which are distorting space and time as they travel around each other. And as they get closer and closer, they spin faster and faster, and the amplitude of these gravitational waves increases. And you can see around the black holes, you have this lensing effect where the stars are all, where the light from the stars behind the black hole is distorted. And on the left here, you see the type of signal that we actually see. So I took this from the detection paper, which was released, I think, on the 11th of February in 2016, which shows the data not only from LIGO Hanford, but from LIGO Livingston as well. And you might be able to see there's a faint line on each trace, which shows the prediction of the wave and the shape of the wave from general relativity. And on the bottom part of this plot, you can see these two signals time shifted to account for the time that the gravitational wave took to get from one detector to the other. And they match up as well as you could hope for. And because Aaron didn't make the sound before, I get to make these gravitational waves. The reason why they're called a chirp is due to their amplitude increasing and frequency increasing over time, and it sounds a bit like this. Whoop. And this is the type of signal that we see in the detector, and this is the type of signal that we hope to see. And I talked a bit about three solar masses being radiated out as gravitational waves. And this is possible due to another one of Einstein's ideas, which is that energy could be transferred into mass and mass into energy by the equation E equals mc squared. Now, if you remember from one of the earlier slides of how much a solar mass is, it's 3 and 30 zeros worth of kilograms worth of mass. The speed of light is about 300 million, and we have to square that and multiply those two numbers together. And the end result is you get a number with a lot of zeros that's very, very hard to even comprehend how much energy that actually is. And remember, the majority of this energy was spread out into the universe in about 0.2 of a second. So these are the most energetic events that you can get in the universe. Well, how much is 3 solar masses worth of energy? Me and Aaron were talking about this when we were writing this talk, and we were trying to find something which could really convey this number, because even to me now, this is still an absurd number. So we know that people on the Earth use a lot of energy. It's one of the driving causes behind climate change. And at our current power consumption for the Earth, you could run the entire Earth for 1 billion ages of the universe. And the universe is 13 billion years old. So you could run the entire Earth on that for 1 billion years, which is crazy. Another way of putting that is if you take all of the stars in the known universe, so there's 100 billion galaxies and 100 million stars in each galaxy, and you add up all of their collective powers that they emit, that's still, the gravitational wave that was released is still bigger than all of that. So these events are very, very energetic. So what did we learn from the first gravitational wave event, 1599-14? Well, we saw the first direct observation of gravitational waves and the first detection of binary black holes. We demonstrated that black holes with masses of tens of solar masses can form in nature, and we also able to test the theory of general relativity in the strong field regime, i.e. close to a black hole. And we were able to make loose estimates of the likely rates of how many binary black hole collisions we should see, and a lower bound on the graviton mass. And a nice summary of all of these discoveries is available in this paper. One of my favorite facts about the first detection is that this caused the arms of the interferometer that are over 4 kilometers to move by 10 to the minus 18 meters. And to put that in perspective, that's equivalent to the distance between the sun and the Earth changing by about an atom worth of distance, or from here to the next nearest star, Alpha Centauri, changing by the width of a human hair, to really put it in perspective just how little these mirrors moved. Onto the second discovery of our one, of observing run 1, was the Boxing Day event, which is a nice holiday present. And this is caused by 2 black holes that are around 7 and 14 times the mass of the sun that merged into a 20 solar mass black hole. This is a bit further away, but really highlighted that we were able to detect gravitational waves, and we were able to see these binary black holes colliding, and that the first one wasn't just a fluke. And because these black holes were a bit smaller, they stayed in the detection band a little bit longer. And now I'll hand over to Aaron, who will tell you about some of the things that we've seen in O2 and O3.
So the second observing run was imaginatively called O2, Observing Run 2, and it ran for 8 months. Now, the sensitivity of the detectors here was broadly similar to the sensitivity of the detectors in Observing Run 1. But what we really managed to do is get these detectors locked and at this operating point, which Sam alluded to earlier. So you've got all of these tables all aligned to this this tiny precision, and keep these mirrors incredibly still, so they're vibrating less than the width of a proton. We managed to do that with 2 detectors at the same time, more of the time. And the reason we're able to do this is we adjusted our control schemes, and we really had more information about what was happening in the detector, what is the state of the detector, and that way we could apply feedback to exactly cancel that and keep the detector locked for longer. And this is what we call coincident times. So we have times where we have both detectors operating, because we need at least 2 to detect gravitational waves. And because of this, we're able to detect 8 more binary black holes and 1 neutron star. But what was really helpful was that Virgo joined, a third gravitational wave detector, joined this observing run 1 month before the end, and the timing couldn't have been better. Because when you've got 3 gravitational wave detectors, it means you're able to triangulate the signal. And so there's a little sketch of this on the left-hand side of the screen. On the right-hand side of the screen, you've got the area of the sky, which the area that we think GW 150914, the first detection, was from. As you can see, it's a huge area of sky, and this is because there are only 2 detectors. After Virgo joined, we observed another binary black hole merger, and this time with all 3 detectors, and we got much better sky localization. And we were able to do this incredibly quickly because we just need to match the time delay between the relevant detectors. And the reason I say the timing couldn't be better is just a few days later, we observed a binary neutron star merger. And the reason the triangulation is really important is because it means that you can very quickly focus telescopes to look at this. So in this video, you can see 2 binary neutron stars, 2 hot balls of neutrons orbiting around each other. As they spin, they release gravitational waves. And when they get very close to each other, these neutron stars become deformed by each other's gravitational field. Now, because these are not quite as dense as black holes, only just, it means that light is able to escape them. And when they collide, a tremendous amount of light is released. Now, we initially saw a burst of gamma rays. I think Sam's going to replay the video. We initially saw a burst of gamma rays from a certain patch in the sky. This isn't unusual. We see bursts of gamma rays all the time. But what was really special was at the same time, we saw gravitational waves coming from the same patch of sky because we had 3 detectors. And this meant that we were pretty sure, not certain, that we'd seen, well, we were pretty sure we'd seen something special because we'd either seen black holes merging and releasing light, which would be very special, but we didn't see that, or we'd seen a binary neutron star merger, and it was the latter. We'd observed a binary neutron star merger. And this is so much science was released from this event. And the reason there was so much science is because we don't have experiments on Earth with gravitational fields as strong as neutron stars. It's not possible. And also on neutron stars, these are really hot balls of neutron stars with in this plasma state where you have lots of really interesting quantum mechanics, lots of really interesting particle physics, and you also have lots of really interesting gravitational general relativistic effects all happening at the same time. And so I can't really go through all the science, but some of my favorite aspects were we confirmed that gravitational waves travel at the speed of light. This was predicted in Einstein's general theory of relativity, but as I said before, any violations to the general theory of relativity would be really interesting. The follow-up observations were observed in every single wavelength of light. Initially, there was a gamma ray burst, and then as these neutron stars cooled, the cloud around them cooled as well. These observations shifted through X-ray, ultraviolet, visible light, and then we observed them in the infrared as well. And this was a period of months that this event was being observed. There was an independent measurement of the Hubble constant. If you're really astute with your astrophysics, you'd know that there's two different measurements of the Hubble constant. And so this is an independent way of measuring this. And so with future observations, we might be able to resolve the difference between these two ideas. But my absolute favorite piece of science that came out of this event, there's no process that we knew of before that would generate the amount of gold that we observe on the Earth. There's way too much gold on the Earth for the astrophysical processes that we knew that would produce it. But by observing the nuclear physics that was happening when these two neutron stars merged, we were able to work out what nuclear reactions were going on, and we found out that this was a major producer of gold. So it's likely that if you're wearing any gold right now, perhaps you're wearing a wedding ring or an engagement ring or something like this, then it's likely that the gold that's sitting around your finger or on your jewelry, in fact, came from a neutron star merger. So on the next slide, I'll talk about some of the events in Observing Run 3. Now, Observing Run 3 finished in March as a result of the coronavirus pandemic. It was scheduled to run a little bit longer. Now, in the next couple of weeks, there's going to be a catalogue paper released, and it's going to talk about all the events in Observing Run 3, and it will either confirm or suggest that they remain a candidate. So for now, there's 56 candidates that we observed in the 11 months of Observing Run 3. And the reason we observed so many is because there were tremendous upgrades to the detector. So the laser power was increased, some of the optics were changed. And as I've said a few times, the quantum state of the light entering from the exit port of the interferometer, that was changed as well using some advanced quantum techniques. Which you can ask us about if you're interested. So we observed 56 candidate events, and one of them was really special because one of them was much heavier than we expected. So there's still a lot to unpack, and this paper was only announced a few weeks ago, and we don't really have time to go into details, but it was a really interesting event because it is officially classed as an intermediate mass black hole. So on the next slide, I'm going to hand over to Sam, and he's going to talk to you about how you can get involved with these detections and find out more about them.
Thanks. So with the start of Observing Run 3, the LIGO and Virgo collaborations at the time decided that they wanted to release these events out into the world. So then any member of the public could then be notified when a gravitational wave was potentially detected. And I say potentially detected because these things aren't confirmed yet by humans, and it takes months worth of data analysis to work out whether we actually saw a gravitational wave or not, given the complexity of the machines. So in late 2018, myself and Aaron were at a conference, and we were sat together in this talk, which talked about public alerts for the first time. And I nudged Aaron and said, "Hey, Aaron, we should build an app. This will be quite fun." And quite famously, and much to Aaron's dismay, I said, "This can't be that hard. It won't take a lot of time to do," which of course put the kiss of death on it, and it took a long time to do, and it was pretty hard. But I also wanted to make it. I had a motivation of making it because I wanted to try and get two of my cousins who were in primary school at the time interested into astronomy. And as Nikki alluded at the start, I wanted to make something to show them that I was actually doing something, and I wasn't just trying to avoid getting beaten at Mario Kart. And to try and get them interested in the thing that I was studying at the time and the thing that I now work on. So we made this app called Chirp, which allows you to keep track of the latest gravitational alerts in hopefully a very simple and easy to read way. And before I continue, I want to thank Sam, Ricardo, and George, who all dedicated tremendous amounts of time to try and make this app possible. So as I said, with the start of the third observing run back in March 2019 or April 2019, the LIGO Virgo Calgary collaboration enabled public alerts. This meant within minutes the public could be notified of an event candidate, which is a potential gravitational wave event, through to their email server. But the problem that I had with this was that they were all sent out by machines, and they were all in a machine-readable format. And gravitational waves, they're not polite. They don't really care what time that we detect them. They're equally as likely to detect them at midday, where it's a nice time to receive one, as it is at 3 o'clock in the morning when you don't want to really be woken up. And I wanted to be notified of this because I'm interested in what we're seeing, but I wanted something that I could glance at my phone quickly, go, oh, it's a binary black hole, that's cool, or oh, wow, that's a neutron star, and then log into my email to then see more details about it. And at the time, no such tool existed which had all that information there in a nice, easy to view way. And since its release in November of last year, this has had about 13,000 downloads on iOS and Android, which I think is pretty good for a fairly niche app. So the image on the right of the screen shows one of the main pages of Chirp. So this is an event that we saw back in March of this year, and it has the sky localization, so whereabouts in the sky that we've seen this event, and things like the distance, what type of event we think it is, and so on. So then this video here should hopefully show you what it looks like when you use Chirp. So there's a big list of all the different types of events that we've seen, with all the different information, so how far away it was, how likely the event is, what type of event it is, and then you have options for 2D and 3D sky maps. And we wanted to add the 3D sky maps because there's a lot more information packed in them than just lines on a 2D plot. So as you'll see here, depending on which event that you choose, the sky map looks very, very different. And has a lot more features in it than you would otherwise think. So when this loads, you'll be able to see this 3D model, which Ricardo has put in a tremendous amount of time doing, and has allowed us to host these on Chirp. And these are generated for every alert candidate that we think we see. So as you see, this 3D model is very different from the previous alert. And right at the center of these, right at the center of this 3D model is where the Earth sits. So you see that based on different events, the localization is very, very different, which I personally find really quite fascinating. So now I'll hand you back over to Aaron quickly to tell you how the app actually works.
Yeah, so this is the bit that the bit that I did. So this is when a gravitational wave passes through the Earth, the detectors observe it. And so what we do is we get a voltage, and this is measured at the sites and sampled by a computer. These computers are continuously analyzing all the data from the detectors. And it's way too expensive for us to simulate a gravitational wave every time we think we've seen one. And so what we do is we have template banks of what we think gravitational waves look like, and we compare the data that comes out the detector to the data that's stored in these banks. If there's a match, then a gravitational wave notification is sent out on the gamma ray coordinate network. This is a network that allows astrophysicists to find out about events which are happening in the universe. But it's a machine readable format. So as Sam said, it's not the best if it wakes you up in the middle of the night. Then what Chirp does is it listens to these gamma ray coordinate network events. It processes this data and it formats a notification, which makes it, which gives you a nice picture, and it summarizes the information. And this is all completely automated. Then we send that notification off to Google, which will deliver it to your Android, iPhone, tablet, whatever. But again, this computing work, I just want to stress, that is the work of the entire LIGO collaboration. It's only this little Chirp bit that is the bit that we added. And so on the next slide, you'll see a snapshot of the network status. Now, unfortunately, COVID-19 has resulted in the observing run being suspended. It was planned to go down shortly after it was suspended for upgrades, and these upgrades were planned to last quite a long time, so I think it was about a year. However, everything has changed due to coronavirus. So if you want more information on when the next observing run starts, you can check LIGO.org. And if you want to be completely surprised, then you can download the app and check it. And one day you'll see that the detectors are online again and they're back in observing mode. And once you see that, you'll start getting events through again, and we should start seeing more and more gravitational waves. I really hope they're not offline for too much longer. I'm just going to hand you back over to Sam. He's going to talk about some of his personal experiences in writing this.
Thanks. So I want to just end this to finish on, because I'm aware that we're potentially running out of time. And I really want to try and encourage anybody here that has an idea for a website that shows off or explains some bit of physics or some maths or chemistry or whatever, to go ahead and just make it. But make something that you really want to use, because you will have to put in a lot of time and a lot of effort to make this thing. I had some very strong personal reasons why I wanted to make this, and I also wanted a good excuse to learn how to make an app, because I'd never done this before. So the app's written in a mixture of Python and React, which before I had no idea how to write those in, how to write in those languages. So this was a great learning experience. And these graphs just really show how long it takes to make something that you're not, I won't say that you're finally happy with, but you're happy enough to show off to the public. So the y-axis on this plot shows the rough number of commits. Many of these were done in the early hours of the morning when we had our own free time, when we weren't doing research. So I want to stress this: making these apps and public engagement things isn't our main job, and we did this just because we thought it was fun. And maybe for Aaron and Sam and Ricardo, it was initially quite fun, and then got a bit frustrating towards the end. And you'll see that there's dips and the amount of work that we put in due to members of the development team submitting their theses and going on holidays after it and taking a good bit of rest. And these two apps took us, the website and the app, took about 7 or 8 months to initial release. But don't let that put you off, because it was a really fun experience doing. Yeah, if you want to download our app, you can either go to the website, which is chirp.bham.ec.uk, or you can download it on the Google Play or Apple Store. And if you go to Laser Labs, to a company of our former supervisor, you can download some more apps to show you about gravitational waves. So thank you, and if you've got any questions, we'll be happy to answer them.
Right, great. Thank you very much, Sam and Aaron. That was a truly fascinating talk. We have had a number of questions coming through, and I don't know whether you can see these, either of you, but I'll read them out anyway, just in case anybody can't see them. So David Walesby has asked a question. Gravitational waves are subject to Doppler, i.e. redshift. What effect does this have on the waves? Does this mean that gravitation from the far corners of the universe is weakened, explaining the lack of deceleration of the universe? So I don't know which one of you wants to take that, but I think
I can maybe answer some of those points. So the question was asking about the redshift of gravitational waves. Yep, gravitational waves, like all waves, are redshifted. And so when we observe events which are really far away, the wavelength will be stretched. And so this means the detectors that observe them will need to have good frequency, good sensitivity at lower frequencies, because these they might start out you'd think orbiting each other really fast, and so producing high frequency gravitational waves. But the redshifting will slow this down. The reason we're not able to observe gravitational waves from the early universe is twofold. One, the large amplitude gravitational waves are at low frequencies, and so we can't observe them because our detector is only able to observe from about 40 hertz through to about 5 kilohertz. And secondly, because they were really far away, and so these waves have decayed just like water waves. And so we would need to improve the sensitivity of our detector quite a bit to detect them. I think that answers the question. Sam, is there anything you'd like to add?
Just that the further away the gravitational wave source is, the smaller the amplitude, and it decays roughly with the distance from the Earth to whatever source that you were trying to detect. That's the only thing, to try to give you an idea of scale.
Thank you for that. Right, second question comes from Douglas Blundell. He asks, if the two black holes are accelerating as they spiral in towards each other, then their individual masses must be steadily increasing from special relativity. Is this increase taken into account in the modelling of the gravitational wave?
I'll start answering this, and then Aaron, if you want to chip in, you can do. Yes, the masses will increase as they're going faster. I believe that's what special relativity says. But also, because they're orbiting each other, they're losing energy at the same time. So you have to take into account this effect and the effect that they're moving faster in the models. And I believe this is what's done in these models. I don't know the specifics about them because that's a whole other area of gravitational wave science. I don't know if Aaron, you have anything to add.
Yeah, I'd add one thing. I'd say that the observed mass increases, so it's with reference to some observer, and that I think is an important point. I trip myself up all the time, and I think a lot of people do, with relativity, thinking about the observer and the different reference frames involved. You have to be very careful. That's all I was going to add.
Thank you very much. Third question actually comes from Nikki Thomas, who wants to know, it looks like you built equipment in Birmingham, but the main interferometers are in the US and in Italy. What practical work on gravitational works took place in Birmingham, or were you mainly analysing the results from LIGO, etc.?
So we do a lot of the data analysis in Birmingham. There's a whole team of people which do this, and not only look at the results that you're getting out of the detector, but then try and predict what types of sources that we can see and what things that we can expect. But the detectors, they're so complicated that you need a whole network of people that have different expertise in different things to look at them. So I think Birmingham made about 700 of these sensors, which were then shipped to both LIGO detectors. And it's something which we had experience in making here. These are sensors that were developed in Birmingham, which are then shipped out because there's only so much that the universities that run the detectors in the US can do. So we can contribute like this. There's also other work that we can do if we go and visit the sites, which before the pandemic I was lucky enough to be able to do. And you can do things like you can do computer modeling of the instruments to try and understand how to make them better and how to make future gravitational wave detectors better. by looking at some of the things that you could improve in the actual system. We talked a little bit about controls, and there's tweaks that you can do to looking at how you can keep the mirrors more stable. This is something that we actively do in Birmingham as well. So there's plenty of things that you can do outside of the detector, but it is a lot easier to do stuff if you're actually there. But you're not. Yeah, you can do stuff.
I think one of the things I'd really like to add is Sam is very lucky and also in his research he's produced sensors for the sites, and Birmingham is actually making these boson sensors again for the upgrade, and Sam's actually developing improvements to this. And this is very similar to some of the optical work. Again, I am developing sensors, and there's a long-term plan that one day these will get shipped out and put onto the site. But the point I wanted to add was that these detectors are extraordinarily expensive and extraordinarily complicated. And so we do a tremendous amount of simulation to design the interferometers in such a way that they sit at the best possible sensitivity you can make. And it's almost always a trade-off when you reach this level of precision. If you make the mirror heavier, you have decreased radiation pressure, but increased stresses on the suspensions, and then that may lead to increased thermal noise. If you increase the amount of light in the arms, then you have increased radiation pressure noise, which moves the test mass around. And if you decrease it, then you have increased shot noise, which is your counting uncertainty at the photodiode. So to reach these optimization points, there's a tremendous amount of simulation. And I think a lot of groups that don't contribute hardware do this kind of work. Birmingham and Glasgow are really lucky because we actually contribute hardware to the detector. We build it and we fabricate it here, and we test it and we design it, and then we ship it out. But we are also very involved in this simulation and very involved with the hardware as well.
Okay,
that's all I was going to add.
Thank you. Yeah, we're getting lots of questions coming through. So the next question comes from Gareth Williams, who asks, is there any information in the non-event signal?
Yes, so what we try and do to build up a confidence, and Aaron, correct me if I'm wrong on this, I learned this a long time ago and my memory's not as good as it used to be, but what we do is we take the signal from two gravitational wave detectors, and you look at how likely it is that the signals came from the same event, and you kind of overlap them and try and match them. And then from time where you don't see a signal, what you then do is you then move this, you move these timelines across and then see how well these two signals match up together. And if they don't match up together as well, then you know that it wasn't just the signal wasn't just a result of random noise, and it was actually due to some gravitational wave detector. If there's anybody that's either watching this now that works on the data analysis or watches this in the future, I am so sorry for butchering your entire experiment. So I'm prepared to be told this is not how it's done, but this is how I believe it. Part of the detection process works.
I've got nothing to add.
Okay.
That was fine.
Okay, next question. Joseph Dutton asks, what causes the gravitational waves to decay?
As the gravitational wave propagates out from the source, you can think of it as a single wave crest as like a ring or a sphere in space. Now that sphere has so much energy in it, and as the sphere becomes bigger in space, then that the energy at each point goes down. And so this kind of decay you see in all branches of physics. If you have ripples on the surface of a pond, as they get bigger, they'll decay. Obviously, in the case of a pond, you've also got friction forces going on, which you don't have for gravitational waves. Strictly speaking, for gravitational waves, they do stretch and squash masses. So there was this idea about using resonant bars a few years ago to detect gravitational waves, and so they do actually lose some energy to those sources, but most of the universe is vacuum, and so we can say that this is moderately negligible.
Okay, thank you. And the next question, again from, well, I'll skip over the next one because Gareth's asked one question and we may run out of time. Kevin Ridley asks a question. Can you say anything about the upcoming LIGO upgrades?
Oh, that's a good question.
Sam, shall I answer this? Because I don't know.
Yeah, you answer it. I don't want to answer it because I can't remember what is public and what isn't public, and I don't want to spill any secrets. So no spoilers from me.
There recently was an upgrade to Advanced LIGO, which has been funded by, I think, definitely the UK, definitely the US, and I think Australia has also agreed to fund this as well. And this upgrade is called Advanced LIGO Plus. You can see there's this imaginative naming scheme. We start with LIGO, then we go to Advanced LIGO, and now we're on Advanced LIGO Plus. So this is using the same kind of infrastructure as Advanced LIGO. So the same vacuum tubes and the same core interferometer, but changing some of the optics and adding some extra sensors. So they will add something called a phase camera, which is something developed in Italy and also in Birmingham. And we'll add a few other nice tricks to the detector, again, just to get more information on this state and keep it more controlled and push down these noise sources. And I think that's everything I can say without spilling too many beans.
So I'd add that there's a number of different word packages, and one of them is to increase the size of the central beam splitter to reduce the clipping effects on that. They're also adding something called a filter cavity to try and enhance the resolution of the detector, I think at high frequencies as well, and they're improving or wanting to improve the coatings on the actual mirrors themselves. That's one of the biggest parts of the upgrade, is to try and reduce the thermal noise, or the random motion of the atoms in the coating. They're trying to reduce that.
I actually forgot something tremendously important, which I'd really like to add, and that's that it's not just LIGO being upgraded. There is also an application for a third generation detector, which would be 10 kilometers arm length. So it'd be way more sensitive, and it would really push the limits of the technology. This is called the Einstein Telescope, and it's going to be like a European central detector, and lots of governments in Europe are supporting this. So this would be really exciting for people on this continent.
Brilliant, yeah, thank you.
I'd add as well that just as one last quick thing, that the Einstein Telescope is something that will be built in the next sort of 10-15 years, and the Advanced LIGO Plus upgrade is something that will happen in the next few years. So these detectors are always constantly being upgraded. So this is a big part of what we try and do, is we try and find new ways to pick a problem in the detector, and then we try and solve it to then reduce the noise or improve the amount of time the detector can stay running.
Fantastic, thank you very much for that. So the really interesting question here from Richard Banner, who asks, what would be the best way to get involved in gravitational wave physics, asking as an undergraduate?
So I'll answer this first, and then Aaron, you can fill in. So I actually did no astronomy at all in my undergraduate. I did very little in my at college, and this is despite my first love of physics being looking through telescopes at the stars. And I just picked different courses throughout undergrad that I found interesting. And gravitational wave detectors, they're so complex that, just learning, basic physics, whether it be astronomy, you can go and do data analysis, group projects, and third and fourth year master's projects with different research groups if you're at a university which does gravitational wave physics. So if you're at Birmingham, I know that we do lots of stuff in instrumentation development. and we do lots of work in working out what stuff that we see. But I think you'd be surprised in what you need to know. I took a course on general relativity, but I can count the number of times that I've used that on one hand, despite us studying relativity. Because I do instruments, I did some programming courses. That never hurts, I don't think. And then I did some fourth years projects in optics labs, which I think really helped. But there's so much stuff that you can do that the best way of getting involved in it is expressing your interest to work on something as a summer student or as an undergraduate project, or looking for PhD projects in universities which do gravitational wave science. And the main bit of advice that I've got is if you're enthusiastic about a subject, and you want to learn about it and you want to discover more about it. I remember back when I first learned about the PhD, which I then later went to do, was in a course on lasers and interferometry that Aaron's supervisor was running. And I'm pretty sure, even if I didn't say this, I was definitely thinking about it. Andreas Weisey was running the course, and he said, I've got some PhD positions open on gravitational wave instrumentation. It was involving improving seismic isolation performance and future gravitational wave detectors. And I remember thinking in my head, I have no idea what any of that means, but I really, really want to do it because I have no idea about it and it sounds like fun. So then I went on and applied, and to use a cliche term, the rest is history. And yeah,
Thank you
that's
very
my
much.
advice, to be interested.
I think we're running out of time for questions, so I think we have time probably for one more, which is Emily Clarkson-Webb has asked, please can you explain what happens to the missing mass when as two black holes combine? Is it released as electromagnetic waves, and is the intensity of what we observe in this EM spectrum important to help interpret what is observed in the gravitational wave detectors?
So this energy is released as gravitational waves. So these are the actual gravitational waves themselves are carrying the energy. When black holes merge, we've not yet detected any electromagnetic waves coming from binary black holes merging, and we don't expect to either. But when neutron stars merge, then yes, there is energy carried away in the electromagnetic spectrum, but the dominant source is the energy that's carried away in the gravitational waves, because it costs such a tremendous amount of energy to stretch and squash space and time. Sam, is there anything you want to add?
No, that's basically it. I think I'd add. The majority is just in gravitational waves. So,
right, that's fantastic.
That everybody's questions.
We're just about to run out of time, so I just wanted to thank very much both Aaron and Sam for a really, really interesting talk. I think we all really enjoyed it, and the amount of questions we got sort of indicates that you had really good engagement from the audience and everybody enjoyed it. Richard has asked me to pass on his thanks. Richard Banner, thank you very much. For those of you who asked questions and didn't get them answered, we're going to take a log of the questions. I hope David Wilkinson's listening and we'll do that. And if Sam and Aaron don't mind and we've got your contact details, we'll try and respond to them afterwards. Sure. Meanwhile, in terms of our future events, you'll see that Nikki Thomas has been pasting into the chat all of our programme. If you haven't been able to see that, then I'll just tell you that our next one is on the Tuesday, the 10th of November, which is David Wilkinson, from our own David Wilkinson from the IOP, who's talking about to see or not to see science, physics and science fiction. And if you go onto the web pages, the events.iop.org, and search for IOP HWC, you'll find details of that talk, which will also have the registration link to take part in that one. In terms of what we're doing in terms of physical versus virtual meetings. Obviously, you'll understand that it's a moving feast at the moment. The current plan is everything up to Christmas. We'll definitely be online as a webinar. There's a good chance everything up till March will be as well, but do keep an eye on it. We have provisional arrangements to meet in January and February onwards in physical venues as well. But we have made contingency plans to deliver webinar versions of all of our program for the rest of the year. So hopefully you'll be able to join us by one form or another. Who knows, we might even be able to do both at the same time. But anyway, thank you all very much for your time. And thank you again to Sam and Aaron. Thank you for Nikki and the rest of the committee who organised this. And we hope to see you all on the 10th of November. Thank you.
Thank you.
Thanks.